Hello.
Hey.
First word. Okay. Hi, calculus people. Just listen. We'll start the screen in just a minute. You can see that this works though. Okay, I can move it. Okay. So remember, like way before spring break, or just day before spring break, we just touched on differential equations.
I do.
Yeah, I don't remember any of that.
That's okay. Yeah, you got your notes.
Oh yeah, was it?
Yeah, I just remember the notes.
Yep. Yep. So we looked at differential. We barely looked at differential equations, just barely. So again, just to recap, it just means an equation that has a function and some of its derivatives in the same equation. That's it. And there's whole classes devoted to learning how to solve differential equations when you get to college. It is fun, but it's hard sometimes. And so we took a look at a couple different properties. We looked at the order. That just means the highest derivative in the equation. And then it's linear or nonlinear. It's linear if all the y's and y primes only have exponent 1 and are not inside another function. They can be multiplied by functions of x, but can't be inside like a sine function or something like that. And I just started talking to you about this technique that we're going to learn, which is basically the only technique that we're going to learn, which is called separation of variables. And so the whole idea is you just get your differential equation, you put the x's on one side, and you put the y's on the other side, and then integrate. That's the whole idea. And so I'll do this example again, just so you can see it. But we had just started to look at, I'll just erase, oh no. So let's say that was the differential equation you were given. Can I get the black pen? Will it go away? Sine x times y. Good question. Okay, and so the whole idea is you just get the x's together and the y's together, and note that you can separate that dy dx. It's like a fraction now. You can treat it like a fraction. So we multiply the right side by dx. And then we divide the y over to the left side to get dy over y equals sine x dx. And then you just gotta integrate both sides. Yeah, I know. So integral of dy over y? Ln y, since it's y's, but yeah, that's the integral. And it's absolute value, ln absolute value y. And I'll put a plus c, because it is indefinite. We'll talk about the c's in just a minute. Integral of sine x dx is just minus cosine x. Oops. Plus c. Okay. So just remember that c is just some arbitrary constant. So like you could label these like C1 and C2, because there could be different arbitrary constants. But then you can't just say the constant goes away though, right? In fact, if you want, the goal in solving differential equations is to get y by itself. So we've got to still get y by itself. That means we got to subtract the c over. And so you could say that C2 minus C1 is just a new constant, C3. So ln y equals minus cosine x plus C3. So it's a new constant. And then how do I get rid of my natural log? E. Exponentiate both sides. Base e. So you get absolute value of y equals e to the minus cosine x plus C3. All of that in the exponent. And by exponent properties, you know that e to the negative cosine x plus C3 could also be written as e to the negative cosine x times e to the c3. And e is just a constant, and c3 is just a constant, so you could just call c4 a new constant, e to the c3. So this is just c4 e to the minus cosine x. Okay. So then y, we have absolute value y equals c4 e to the minus cosine x. Yes, sir.
Go back to how you got the C4.
Yes. How did I get the c4? So I just noticed here that e to the c3 is just a constant.
Oh, okay.
So I just called it a new constant, c4. Okay. So then what do I do about an absolute value y? God bless. How do you, have you ever done that before?
No.
Okay, for those, oh man, that's too bad. How do you solve absolute value of x equals 1?
That's a minus 4.
Right. And that's true because absolute value of 1 is 1, and absolute value of negative 1 is 1. So when solving an absolute value, careful, solving an absolute value, you can just say y equals plus or minus c4 e to the minus cosine x. Because if it's positive, absolute value of that, still positive. And if it's negative, absolute value is still positive. So either one will be fine. But let's see. Wait. Where are my notes? I guess I should just leave it there. Well, no, I'll go a step further. This, in order to really get the exact solution, this is what's called the general solution. So this is the general solution. If you wanted the particular solution, you would need to know some point on the curve. You need to know some point on the curve. You need to know an initial value. And then you could plug in for x, plug in for y, and solve for c, and you'd have your solution. So that would be our general solution. What do you think? Clicking? I think you'll find it to be a lot of fun once you get into it. So let's do some problems. Okay, so example, solve y times dy dx minus x equals 0. Maggie, step 1, what do you think?
Add the x over.
Sure. All right, now other Maggie, step 2. Divide the y? Well, if we divide the y, what we would have is this. Let's do that instead. Because the dy and the y are already together. So let's keep them together. Okay, y's are together, x's are together. Let's integrate. Alright. On the left side we've got 1/2 y squared plus c equals 1/2 x squared plus c. And if you just keep in mind that there has to be some constant added, you can just drop one of them, right? You could just drop the one on the left because you'll still have some constant accounted for. So then you just gotta solve for y. So multiply everything by 2. So y squared equals x squared plus, you could say 2c, but again, you can just think of it as a constant times a constant, so it's absorbing that 2. Like that. And then solve for y. So then y will equal plus or minus the square root x squared plus c. Yes, ma'am.
I have a question. Why were you able to get rid of one of the c's in this example but not in the other one?
Sure. So in the other one, I was kind of trying to draw things out so you could see what's happening. That really, it's just some constant that you just need to be aware of where it is. But you could take all this trouble to make different C1, C2, C3, C4, but really in the end, it's just some constant. So you can just leave it as C and just make sure to carry it around where it's supposed to go. Does that help?
Yeah.
Okay, good. So that's what we're left with. Any questions on that? So this here is a family of curves. So again, it's a general solution because it's got that C. It's a bunch of curves. So when you plug in, if you put in C equals 0, you get one curve. If you put in C equals 1, you get another. C equals -1, you get a different curve. So it's an infinite set of curves, a family. I was just thinking the same thing. The anticipation is building. Show it to us. So, okay, I do want to. Let's start at 0. C equals 0. Okay, so what you have, if C is 0, then you have square root of x squared, which is just absolute value of x. So you get the plus in red and the minus in green. But if you move that C around, well, just if I hit play, oh, it will do it. Okay, that's kind of neat. But if you move it around, like C equals 1, you have a hyperbola. And then just the hyperbola shifts around, right, as the C's change. So it's those infinite set of hyperbolas. And then when C gets negative, it's pretty cool. It just is a horizontally oriented hyperbola. So all of those are solutions to that differential equation. And to figure out which one is your solution, you need to know a point. And then you could solve for C and figure out which of those curves it is.
Can you throw that negative sign in plus percentage?
Oh yeah, let's just see it all. So satisfying.
Wow.
Oh, it goes back too.
Wow.
Yeah, new screensaver.
Like that thing where just, like the ball thing where it just keeps going back and you just watch
Yes.
I
Yes.
guess you could just like narrow the recording window to just that and record a screensaver.
We can make the speed faster.
Oh.
Well, we probably want it slower, right? If it's going to be soothing.
You see how fast it'll get though.
Oh, you want to see how fast it goes?
Yeah.
That's the best one.
Wow. You're welcome, video people.
I forgot about that.
Can't forget about them. They're there. Just because you can't see them doesn't mean they're not there. Actually, they're not there. They're not there. They will be there, but they're not there. Okay, so let me give you one to solve. Let's see how far you can get. So solve the initial value problem, IVP initial value problem, y prime equals negative ty with the initial condition y of 0 equals 3. So see if you can do it. You might need to rewrite y prime as dy dt so you can get started. Initial value problem.
What's the first step? Or is that?
Rewrite that as dy dt.
This is good so far. As long as you're here.
Yep.
Here.
So I think if I differ the logarithm. And just make sure that that's c is exponent. Right? You yes, exponentiate both sides. Yeah. Nope. So you can use your exponent properties, that's really a couple problems ago. So you would minus 6 over 2 plus c, which is a thing kind of minus 6 over 2 times e to the c, so then we just let e to the t be a constant. Okay.
So the plus and minus, you just solve it.
So first, let's see if it's in
It is, it's just.
okay. Okay. And then so what I recommend doing is just like we rewrote it instead of like we just kind of see outside.
Oh.
That'll make it easier to solve. Yeah, it is. There's an easier way to write it though. Than that.
Or would you like take that into?
I suppose I would, but it might make it harder for me to solve multi-step problems or if you use like what you do. But I mean, technically it's correct.
I'll let you.
Right. All right, so step one would be to rewrite y prime as dy dt equals minus ty. Get the y over to the left side, dy over y equals negative t dt. Then integrate both sides. So that'll get you ln, absolute value y, equals negative t squared over 2 plus c. Then you got to exponentiate both sides, so e to that and e to all of this. So absolute value y equals e to the minus t squared over 2 plus c, which you can just write as c e to the minus t squared over 2 by exponent properties. So you're looking at something like that. And then when you try and solve it, so you have that initial condition given above that y of 0 equals 3. So you plug in 0 for t and 3 for y. So 3 equals plus or minus c e to the 0. And so that's c times 1. And so really what you do is you drop the plus or minus and you only take a positive. You just take a positive 3. Because you want, what you're looking for is you want it so that whenever you plug in 0 for t, you get a y equal to 3. So you don't want plus or minus 3, you just want 3.
How did you get the c from the exponent?
Okay, how do you get the c from here to here? That's like what we did earlier, where you use your exponent properties, e to the minus t squared over 2 times e to the c. And e to the c is just a constant, so you can write that as e to the minus t squared over 2 times c. Just a new constant. But I'm dropping all the subscripts.
Wait, so why can't you do minus 3?
Because if you did minus 3, then when you plugged in t of 0, you get minus 3 times 1, which does not equal 3. Yeah, so the initial condition does lock you into one thing. So we get c equals 3, and we get a final answer of just 3e to the minus t squared over 2. And not the plus or minus. We do drop the plus or minus at that point. So that's an initial value problem. So you can solve lots of things. Okay. So now, that's some of the basics of separation of variables. And like I said, that's the only real technique we're going to focus on for differential equations. But we will look at some applications, because you can do some pretty neat stuff with just that.
There you go.
For those of you watching it, you'll have to get the applications of differential equations example sheet downloaded from Moodle. Okay. So one of the things you have to work on is being able to translate word problems into a differential equation. So like this first one, for example, Michael, would you read it for us, the first one?
The population of the country is growing at a rate proportional to its population. If the growth rate per year is 4% of the population, how long will it take the population to double?
Okay. So this is a differential equations problem. And so the key words here is that the population is growing at a rate, so that's like a dp dt, so the rate of change of population, growing at a rate proportional to its population. So just very generally what that would mean if you just had that amount of information would be that dp dt, the population, the rate of change of population over time, would be k times p. If that's all you had. But then they tell you if the growth rate per year is 4% of the population, so then we know what k is, based on what they just told us. It's 4%, so then we know that this is actually specifically 0.04 p. And so we want to know how long will it take the population to double, but that means first we need to get an equation for the population as a function of time. So we want p as a function of t. Population is a function of time. And let's see. Well, okay, so this is, again, it's just separation of variables. So we start off by bringing the p over here, bring the dt to the other side. We integrate ln absolute value p 0.04t plus c. Exponentiate both sides. And hopefully you can see what we would get is this, p equals c e to the 0.04 t. So they didn't give us a number on the initial population. But it might be helpful just to be able to put something in there to stand for the initial population. So let's do this. Let's call p at time 0 p naught. So then that would mean if we substitute this in here, we would get p naught equals c e to the 0.04 times 0, or just c. So c equals p naught, and p of t equals initial population times e to the 0.04 t. And so what, this is kind of neat. So it's saying that when the rate of change of something is proportional to the value of that thing, you get exponential growth. And so this is it's like, if you ever felt yourself wondering in pre-calculus at all, like, where does that e come from? Why are we dealing with e, special natural number? It is the number that comes out whenever a rate of change is proportional to the actual quantity itself. So there it is. There's e coming up in nature like that. So this is an exponential growth equation. So population is growing exponentially at a rate of 0.4 of the current population per year. So we want to find out when the population doubles. Any thoughts as how we can do that? P naught is 1, P of t equals 2. Okay, that's one way to do it. Yep. You could also figure out, if you want to keep it more general, you could say, when does P of t equal to P naught, right? Because that way it leaves it totally general. If P naught's the initial, you get the same result as you said though, Maggie. So then you end up setting P naught e to the 0.04 t equal to 2 P naught. And P naught divides out from both sides. And here you are trying to solve this exponential equation. So you have to log both sides. So you get 0.04 t equals natural log of 2. So t would just be ln2 over 0.04, which is about 17.33 years. I know.
Now I know exponential growth and decay function.
Yeah, it comes from differential equations. That's one place it comes from, differential equations. But you do see it all over the place. So this would be an exponential growth, right? The population's growing, but you could also imagine a decay curve, and we will talk about one decay curve. But maybe like you're seeing some pattern here, right? Like we keep getting natural log y or natural log p equals this. The final solution is just an exponential, right? So we got that here. We got that for this population one. We got it here in some way. It's a little bit different here because it's it wasn't just proportional to itself. Notice that this equation was proportional to y times t, not just a constant. But I will give you the general solution. You can see that hopefully in general, if you have dy dt is just some constant times y, you, like as we showed in the last problem, you could show that dy over y equals k dt, integrate, and you end up getting to this step where y equals some initial value, y naught, e to the kt. So when you have functions of this form, you do get this solution. So good to know, because you will see it a lot. All right. And I think I'll save the other example for Monday, and I'll just go ahead and give you the differential equations homework now, so you get a head start on it. It'll be due on Tuesday, but I'll let you go ahead and get started.